Bismillahirrahmanirrahim. We come to the second part of this lecture, which is the volumes of solid obtained by revolution. We define the volume, or how to find finding the volume for a solid as V equal to the integration of the cross-sectional area AX over AB. If we are given S be a solid that lies between X equal to A and X equal to B, now if the cross-sectional of S in the plane BX through X and perpendicular to the X-axis, or in some cases Y-axis, is given by A sub X or A sub Y, or A of X or A of Y. Where A is continuous function, then the volume of S is given by the integration A to B of the cross-sectional area. For example, suppose that we need to find the volume of the solid obtained by rotating the region bounded by the given curve about the specified line. Suppose that we have this example that we have y equal to x plus 1 and y equal to 0, x equal to 0, and x equal to 2. We need to find the volume of the solid obtained by rotating the region bounded by the given curve. So in the first step, let's graph the function, or let's find the bounded region R. I have y equal to x. Y equal to x, this is a linear equation. We can find 2 points, x equal to 0 and y equal to 0. To graph it, I will have y equal to, when x equal to 0, y equal to 1, and if y equal to 0, x equal to minus 1. So it is a straight line. This is y equal to x plus 1. Now for the second one, I have also y equal to 0. Y equal to 0, this one, is the x-axis. And we have x equal to 0, to this line, vertical line, and x equal to 2 will be this line. So my R is this area, this region. This is R. It's actually between the curves. Now, if we need to rotate this about the x-axis, we are graphing a typical rectangle like this one. And rotate about the x-axis. So I will have a shape, a disk like this one. So the graph will take something like this, which is the cutted cones. Now the integration for, or the volume, or I can say more general, this is the shape of the figure, but we start from 0, not from minus 1 to 2. I will have something like this one, but this is cut as 0 equal to 1. And the cross-sectional area will be, is a circle. So AX in this case, since we have a disk, you remove these. This is the R, the radius of the cross-sectional area. This one. We denoted by R is equal to the function y itself, which is equal x plus 1. Because we know that the volume is given by AX multiplied by the delta x. And AX in this case is equal to y, it is the area of a circle. by r square multiplied by, or just let's say ax, that's equal to by multiplied by r. R is give me the height of this rectangle, which is denoted by y. I can say y1 minus y2, that is equal to y1 is x plus 1 minus y2 is equal to 0. Again, I have y1 and I have y2. It is the height of the rectangle. This will give me the radius of the cross-sectional area. So it is y multiplied by x plus 1 square. So the volume, which is given by the limit from 0 to 1, given in the problem, of ax dx, that's equal to 0 to 1 of y x plus 1 square dx, or cannot by outside the integration from 0 to, let's say 0 to 2, not 1, given 2, not 1. This is 2. Of x square plus 2x plus 1 dx. We just expand the binomial x plus 1 to power 2. It is x squared plus 2x plus 1. Now integrate and evaluate. I will have by multiplied by. The first one is x to power 3 divided by 3 plus x squared plus x from 0 to 2. Just find the value for this one. We'll have by multiplied by 8 over 3 plus 4 plus 2, which is equal to 26 by over 3. And we can just write general unit to say cubed unit. So this is how to find the volume of a region or solid obtained by rotating a given region, R. Let's have another example. For that, I need to find the volume for this region, x equal to square root of 5 minus y, and y equal to 0, and x equal to 0 about the y-axis. So in the first step, this graph, the function I have this time, x equals square root of 5 minus y. 2, 3, 4, 5, and it's to go down like this. This is x equals square root of 5 minus y. And y equal to 0. Is this one? This is y equal to 0. And x equal to 0 is the y-axis itself is x equal to 0. So this is my region, this is R. And I want to rotate this one about the x-axis. It means I'm going to graph a horizontal typical rectangle. And rotate it about the y-axis, I will have a disk like this one. This is a disk. And R, this is R, which is equal to the height or the length of the rectangle. Since it is horizontal one, so we say that the right curve minus the left curve, R will be given this time as x2 minus x1. x2, I can say the right one, you put x1 and x2. It is the right curve minus the left curve. So it is the square root of 5 minus y minus 0. So it is 5, or square root of 5 minus y. or can say AX, or no, not AX, it is AY this time, is given by R square, which is equal to by square root of 5 minus y to power 2. So we can have this shape. This is the solid. So my graph is this one. Rotated about the y-axis, we have this shape. This paraboloid in three-dimensional case. The cross-sectional is a circle, like this one. It's given by r square, and r is equal to square root of 5 minus y. So ay is given by r square, or by 5 minus y, or to power 2, or just make it as y times 5 minus y. Now the volume for this one, we start from y equal to 0 up to y equal to 5. So from 0 to 5 of a y, this is volume, equal dy. Because we are rotating about the y-axis, not the x-axis. So it is dy, which is equal to 0 to 5 of y multiplied by 5 minus y, dy, which is equal by multiplied by integration of 5 will give me 5y minus 1/2 y squared from 0 to 5. Using the fundamental theorem of calculus, this will give me y multiplied by, replace y by 5 or substitute y by 5, I will have 25 minus 25 over 2 minus 0. So the lower limit is equal to 0 there. This will give me 25 y over 2 cubed unit. So this is the idea of finding the volume of a solid by rotating the region about the x-axis or y-axis.